Hello everybody. So we're going to get started here and we're going to learn about Chapter 1, An Introduction to Statistics. So you can print this note page, this blank note sheet, off on Canvas, and I would suggest you print it out, fill it out as we go, or if you have a program where you're able to annotate the document, you could do that as well. So just on your computer. So Introduction to Statistics. The first chapter covers a lot of basic vocabulary, so it's not much of a math class as it's going to seem more just learning vocabulary. And then we'll jump more into the math of things in Chapter 2. But with that being said, Chapter 1 is very important because it's very important to have a foundation of statistics and the vocabulary that we're going to use before we actually start doing the math with the statistics. So first of all, the first thing we're going to learn about is basically data, which consists of information coming from observations, counts, measurements, or responses. And from data we get statistics. So that's the science of collecting and organizing, analyzing and interpreting data in order to make decisions. All right? And basically, there's two kinds of data that we can have. There's a population and there is a sample. And the distinction between population and sample is very important. So a population is a collection of all outcomes, responses, and measurements or counts that are of interest, and a sample is a subset of a population. So many times, if this box represents my population, okay, so this represents my population, and then many times we can't get a hold of the entire population. The United States tries to do this every 10 years, right, with a census. So they try to survey a bunch of different people, and it's impossible to actually survey an entire population of individuals if it's a very large population. Now, let's consider the population of, I don't know, the grades of everyone in this online statistics class. Well, this online statistics class isn't that large. It would be pretty easy for me to just get a population of those outcomes and responses. But most of the time, we want to find data about an entire population. And because of that, we get a sample, which is a subset of that population. And the whole point, I don't know about the whole point, but a lot of statistics is basically using the sample to make inferences about the population. So we use the sample to try to find things out about the population or estimate things about the population, because finding information about an entire population is kind of impossible. So what I want you to do is read the next couple examples and try to figure out what the population is and what the sample is on your own. So maybe pause the video here and try to do that. Okay, so you probably pause the video hopefully and try to figure out what the population and the sample is. So in the first one it says, in a recent survey, 1,708 adults in the United States were asked if they think global warming is a problem that requires immediate government action. 939 of the adults said yes. So the population is the responses of all U.S. adults. And the sample is the responses of the 1,708 adults surveyed. So the responses of all the adults is what you're actually caring about, and that is the population. Now we can't ask every U.S. adult, so what do? We get a sample of the 1,708 adults. Now a common thing to mention is this 939, and some people say that's the sample, but no, the 939 are just the portion of the sample of the adults that in the sample that said yes. So that is neither the population nor the sample itself. All right, so using that same principle, let's go to the next one. The U.S. Department of Energy conducts weekly surveys of approximately 800 gasoline stations to determine the average price per gallon of regular gasoline. On February 12, 2007, the average price was $2.24. So in this one, the population would be the prices at all. And it's always a good idea whenever you identify the population make sure you say the usually word all or every, something that says you are surveying or identifying everybody in a group. All U.S. gas stations. And the sample prices at, and it looks like there's 800 that were surveyed, at the 800 gas stations surveyed. Okay, so that's population and sample again. Population is everything, sample is only a part. Okay, let's move on. Again, this is a very key thing, so make sure you remember that. Now, for population, what is a description of a population? Well, that's actually a parameter. For sample, what's a description of a sample? Well, that is a statistic. So when we hear a statistic, that's actually only part of a population. For example, let's say you hear a statistic something like the average height of a U.S. citizen is 5'9" or whatever it is. Well, did they actually measure every single U.S. citizen's height and find the average height? No. They got a representative sample of a group of from the population of all U.S. adults and got that average height and said that was the average height of everybody. So it's not necessarily lying, but that's just how statistics work. So whenever you see a statistic, you have to keep in mind that it's actually an estimate of what the actual height or what the actual parameter is. Statistics are used to estimate parameters. Also, to keep these straight, notice that population starts with the letter P and parameter starts with the letter P, sample starts with the letter S, and statistics starts with the letter S. So let's determine whether the following statements are a parameter or a statistic. So once again, I advise you pause the video here, try to figure this out on your own, and then watch the rest. So hopefully you tried to figure these out on your own again. So we have a recent survey of a sample of MBAs reported that the average salary for an MBA is more than $82,000. Again, it says of a sample, so right away we can say statistic. Whenever the description has the word sample in it, we're going to say it's a statistic. What about the starting salaries for the 667 MBA graduates from the University of Chicago Graduate School of Business increased 8.5% from the previous year? So this one is actually a parameter because it's talking about all the graduates from the University of Chicago. How do I know it's all the graduates? Well, you have to be careful here because in statistics, whenever you read problems, and you'll find this as you go throughout this course, just one small word can make a difference. And the small word here is the. If it's the 667 graduates, that is it. There's no other graduates besides the 167 graduates. It doesn't say it's a part of, this group is a part of all the graduates. That is it. So this is a parameter. And then the last example for statistic and parameter, in a random check of a sample of retail stores, the Food and Drug Administration found that 34% of the stores were not storing fish at the proper temperature. Once again, this problem actually says sample, so we can say this is a statistic. Now, keep in mind, it doesn't have to say the word sample. For example, it could say a representative group from all whatever you're talking about, and that would still be a statistic because a representative group from everybody is a sample. So just keep in mind that statistics have to do with samples, which are a part of a whole group. Parameters describe populations, which is everybody in a group. Okay. After this, you determine the distinction between statistic and parameter. There's basically two types of statistics. The first type of statistic is what we're going to be primarily dealing with in this course, and that's descriptive statistics. And descriptive statistics is really what you're used to. So whenever you see like a chart or graph that summarizes data, or whenever you see like an average of some kind, those are all descriptive statistics. However, inferential statistics is a branch of statistics that involves using a sample to draw conclusions about a population. And A basic tool to utilize inferential statistics is probability, which is why this course is probability and statistics. So what we're going to focus on in the first 2 chapters is descriptive statistics. Then we're going to focus on probability for 3 chapters. And then we're going to combine those 2 concepts, and in the last chapter we're going to do a little bit of inferential statistics. Because this is only a semester course, we're not going to get super deep into inferential statistics. So you could actually take AP statistics and that gets more into that part. But for now, we're just going to be focused on descriptive statistics and probability, and then a little bit of inferential. And so let's do a couple examples of the difference between these two. So it says, a large sample of men aged 48 was studied for 18 years. For unmarried men, approximately 70% were alive at age 65. For married men, 90% were alive at age 65. So we need to determine what is the descriptive branch of statistics here, and then after we read the description, what is an inference that we can draw using inferential statistics. So first of all, let's start with the descriptive statistics. So we'll write descriptive. And there's really 2 different descriptive statistics here. One was, and I like to start with the percentage, 70% of unmarried men were alive at 65. And same thing, 90% of, but it's married men, were alive at 65. So that's the descriptive statistics. And what's the inference or inferential statistics? And at this point, it doesn't need to be something that's absolutely true. But basically, what conclusion could you draw from this? Well, there's a couple things you could draw. You could just say maybe married men live longer than unmarried men. Which isn't necessarily true, right? Because even though a larger percentage live to 65, they may actually live, they may not actually not live as long. Also, this is just a generalization, right? So if I pick a married man and an unmarried man, that's only one from that group. So you can't say, well, that married man's going to definitely live longer than that unmarried man, because you don't know their background, right? These are just generalizations. So this is just an inference that we can make, and this is what happens on average. It does not need to be absolutely true. You could make an inference to something like, well, maybe married men are healthier than unmarried men on average, and that's why they live longer. Sure, that's an inference you can make too. So there's not just one answer here that's necessarily correct. It's just something that you think is right from the descriptive statistics. So what's a conclusion you can make from those descriptive statistics? So let's do the next one. In a sample of Wall Street analysts, the percentage who incorrectly forecasted high-tech earnings in a recent year was 44%. So again, we'll go to descriptive. Differential. So the descriptive statistic here is the percentage, right? So I always like to start with the percentage. So 44% of Wall Street analysts incorrectly forecasted high-tech earnings. Okay. What's an inference you can make from this? Well, maybe just if you know anything about Wall Street and stocks, high-tech earnings. And keep in mind, this is 44%. That's almost half of Wall Street analysts, which this is basically their job, is to forecast what's going to happen. So if half of people are professionals and they're bad at doing, and they're not, correctly forecasting, well, high-tech earnings are difficult to predict. It may just be a difficult job. you can make some other possible inferences as well. Maybe you want to say something like, I don't know, maybe Wall Street analysts maybe they need to be trained more, for example. Maybe they're just stupid. I don't know. You could say a lot of different things. Again, we're just using the descriptive statistic to make an inference. It doesn't need to necessarily be right or wrong. Now, what you can't say, and this is important, for inferential statistics, it has to take the descriptive statistic and draw a conclusion. For example, an incorrect inference, this is not an inference, saying something like, almost half of Wall Street analysts incorrectly forecasted high-tech earnings. Well, that's not an inference, because that is basically just restating the descriptive statistic. So you have to make sure that the inference you're making is actually an inference and not just restating the descriptive statistic. Notice how my inferences are actually using that statistic to draw a conclusion. Okay, so that's descriptive and inferential statistics. And the last section, or the last thing we're going to learn, is data classification. There's many types of ways you can classify data. We're only going to be concerned about qualitative data and quantitative data. So the first is qualitative. Second is quantitative. And qualitative data consists of attributes, labels, non-numerical entries, and quantitative is a quantity, so it's a numerical measure of count. Basically, it has to be a number of some kind. So again, try on your own, read the 3 examples and classify just as qualitative or quantitative. And remember that quantitative data isn't just a number. That number has to actually measure or count something. Okay, so try to do those 3 on your own. So hopefully you did those 3 on your own, and let's go through them. So the favorite colors of people in your statistics class, that would just be qualitative, because a color is just an attribute of some kind. The ages of people in your statistics class, so that's actually measuring how long you've been on Earth, right? So that number does measure something, so that is quantitative. And the jersey numbers of the Chesterton basketball team. Well, this one's qualitative, because even though it's a number, that number doesn't actually measure anything, right? So the number, remember, has to measure something. Right now, think of a few other examples that are qualitative but are numbers. So again, maybe pause the video and I'll give you a few other examples. So some other examples like phone numbers, your social security number, your school ID number. All of these are numbers that really just identify you or whatever you're talking about, and they don't actually measure anything. So that's just something to keep in mind. All right, and that wraps up our first statistics video. So I'm going to stop it here, and then we'll move on to section 1.3, which is experimental design.